So first of all, Philip, if you could come forward, please. Great. So the way this is going to work, there's going to be 2 minutes per talk. 2 minutes, that's all you get. So I'm going to start a timer when you start speaking. And if you go over 2 minutes, I'm just going to ask the audience to thank you, and they're going to start applauding, and then you're going to leave. So before each speaker, we'll have the name and then the next speaker. So if your name is Albert Chan, you should probably come up to the front too so that you're ready to go as soon as Philip is done. And with that being said, our first speaker is Philip.
Yes, hello, thank you for having me. I would like to present my project briefly. We're trying to make the blockchain ecosystem in general more accessible. So what we have at the moment, many different protocols, many different contract languages, they are portable. The vision that we have is like a uniform operating system. So think of a terminal where you can log in with your user, you have a user folder, and all this happens like in a standard POSIX environment. This is the far goal that we have been pursuing, and the structure we have come to is a data structure. It's not about the protocol, but it's about the structure, and all the proofs that we're doing is related to this structure. It's a heap, so it merges, the protocol itself merges ideas of proof of work, proof of stake. A property of the protocol is you can add a work once and then use it at a later time as stake. The advantage of this is that we don't need an application layer in order to redeem stake. This makes the protocol simple. And thing we achieve is a very low-level protocol which combines like functionalities of reputation systems, prediction markets, and consent systems in one simple protocol. The blocks are 5 tuples, so it's really not very complex. The operations are in constant time, and the algorithm, in order to insert and get data out of our block heap, I forgot what I was to say. And yeah, the final goal that can be achieved with this is like a one standard API, where you can start from different machines. It's completely decoupled from the application layer. We can use JavaScript, we can use bare machine code, and the security is ensured by the protocol itself. One effect that we like very much, and which was like a goal of us, is that based on this system where blocks are assigned and where identities exist, we can implement a universal basic income very easily. And we are currently implementing the reference implementation. The paper will be finished like within 14 days. You can check the name out, and I'm happy for you to attending me. Thank you.
Great, that was about exactly 2 minutes, so let's thank Philip. And next up we have Albert and Ashley, if you could be ready, please.
Hello everyone, I'm Albert Chan, and I'm the CTO of Injective Protocol. So we are building a fully decentralized and front-running proof DEX, which enables trustless liquidity sharing. Now the way this works is that we match and execute trades on a layer 2 sidechain, which prevents front-running using verifiable delay functions, or VDFs. So the nodes on our sidechain aggregate orders per block and then submit them to 0x for actual settlement. They also serve as relayers, which also share liquidity in a trustless fashion. So this, of course, allows for more liquidity, more efficient spreads, and a better DEX experience. Now, to go into a bit more detail about how we prevent front running, I'll walk through a simplified example of a trading scenario where 2 traders submit the same order at 2 different times. Now, suppose at the beginning of block 1, taker A sees an order from the order book and wants to take the order. So he begins computing a VDF time proof on top of a hash of the order, and then continues to submit it until the end of block 2. Now suppose later on, taker B decides he wants to take the same order. So he begins computing a VDF time proof and also submits it to the sidechain. At the end of the block, the sidechain will then determine the correct sequence of orders based off the VDF time proof length, where orders with longer time proofs are prioritized first. Now since the front runner can't create a longer time proof, he won't be able to beat taker A from taking the order. Now, for time purposes, this is a very simplified model of how our protocol works, but we also use commit reveal, both interactive and non-interactive, and prevent against grinding attacks, and we also plan to integrate VDF ASICs in the future. Thank you.
Okay, thanks, Albert. That was a great demonstration that you don't have to use all 2 minutes. Ashley.
Hi everyone, my name is Ashley Landquist. I work at the World Economic Forum on our blockchain and distributed ledger technology team there, which is located in San Francisco, which is the tech headquarters of the forum. Previously, I was at UC Berkeley and blockchain at Berkeley. I thought I'd share with you a project that we're running at the forum, which is trying to use Ethereum and smart contracts to reduce corruption in the public procurement process. So public procurement is actually the largest source of government corruption in the world. About $2 trillion is diverted annually from global taxpayer funds and development aid to line the pockets of corrupt officials. So what we're trying to do is develop a pilot, and it's in partnership with the government of Colombia and with the Inter-American Development Bank. And we'll run this pilot over the summer in a live procurement process. We're specifically designing this in a public permissioned Ethereum environment where citizens and journalists and the public can review a procurement process after it happens to evaluate and sniff out any fishy activity and hold the participants accountable. But the participants in the system are in permissioned nodes, and they're the vendors, the bidding agency, and the government. So we're trying to see if the censorship resistance, transparency, and automated smart contract functionality of Ethereum and smart contracts can help with the situation in procurement. On the left, you'll see a bunch of locations where corruption tends to happen in the procurement process. So we're specifically designing to solve for some of these. And we're operating in a very multi-party process where we have a lot of support from technical experts like QuantStamp and from academic experts and economists to support this as well and design the best solution that we can. Thank you.
Very much. Okay, so next up we have Pedro and then Stefan.
Hello, my name is Pedro Moreno Sanchez, and if you ask me, actually, I'm really surprised by the amount of advances and different challenges that appeared in the last 6 months. So I'm pretty sure that in the next 6 months, there will be many other technologies and many other things happening. So if you really want to know about them, I have the solution. So it's the International Blockchain Summer School that we are preparing in Vienna. So it will happen in September, the first week of September. Vienna has been chosen as the most livable city during the last 7 or 8 years in a row. So if you have never been, you should actually definitely think to come. And if you really want to learn about blockchain technologies and the security and privacy of them, we are preparing a excellent lineup of speakers that will tell us about the cutting-edge research of security and privacy problems, blockchain and distributed ledger technology, as well as we have keynotes and hackathons from the leading companies in this area. This thing is being organized by leading researchers like Matteo Maffei from TU Vienna, Edgar Weipel from SBA Research, Kevin Borgolte from Princeton, Martina Lindorfer for TU Vienna, and yeah, myself as well. In order to organize that, obviously we need sponsors. For that, we offer a couple of different packages. We can offer you to talk in the main program if you are interested. You can also host a practical session in which you can show your technology and teach the students and the attendees how the technology works, and obviously speak with them and have social interactions with them. These are only some proposals, so if you are some other proposal, please talk to me. We have many other choices. And yeah, if you're interested, here's the website, contact this email, and you can contact me also in this Twitter handle. Thank you very much.
Thanks, Pedro. So Stefan, and then actually Adam is not here, he told me, so sorry to spoiler alert, but Emily, if you could be ready after Stefan.
Hey everyone, I'm Stefan. I'm the systems architect at Numerai, and what I'm going to talk about is libsubmarine. So libsubmarine is an implementation of submarine sends, which is a framework for preventing transaction reordering attacks on Ethereum. Those attacks can affect stuff like front running. And this library allows anyone to do things like seal bid auctions and temporarily hiding transactions on Ethereum. So the way that it's implemented is quite similar to a traditional commit reveal, except that the commitment is hidden by a large anonymity set. And so there's kind of this anonymity attached to the commitment that the miners are not able to observe. This implementation is standardized kind of in the same approach as an Open Zeppelin library, and you can find it by looking at libsubmarine.org. There's both a on-chain and off-chain component to it where you have to generate a proof off-chain and then submit it along with the reveal. But all that is already figured out and is ready to be implemented in your project. Thank you.
Thanks a lot. Okay, so Emily, we'll have you go now. Too bad we missed that. That looked like a lot of fun. And then Carl will be next.
Great, thank you. Hi, everyone. Are we, okay, so hi, my name is Emily Pillmore, and I am a Haskell engineer with Cadena. I am also the lead maintainer of the Pact smart contract language, which is a Turing incomplete, formally verified language targeting the Cadena stack. So today we'd like to announce the fact that we've actually incorporated the notion of theorem proving with interfaces. So sort of like your Java style or your Solidity style interface. But you can actually specify the laws that you would like the functions that you're going to ask people to implement directly in the interface itself. So for instance, you can say things like, my transfer function should be mass conserving. We want the amount credited to the receiver to be the amount debited from the sender. This is not a common thing that you get just by specifying the function signatures for a given function. You need additional structure in order to enforce this. And what we want to leave you with here after this lightning talk is the question of what do we want people to implement and what do we want to enforce as invariants of the programs that we write on the blockchain. So for instance, if I want every balance to be greater than or equal to 0, I can do this with a type, or I can write a model that satisfies that all balances in my contract are greater than or equal to 0, or greater than 0. Or I can talk about custom escrow behaviors where, after so many steps, certain invariants must hold. Or relationships between functions and the data, like sending X many dollars to you and you sending them to me means nothing happened. Or proportions of funds that go to owners and stakeholders in some contract, according to some distribution that you write. So for instance, just as a sort of low-hanging example that you can all think about, blackjack. It has rules. You can talk about anteing must be greater than 0. At each round, a user can bet greater than or equal to $0. If you hit 21, you win, and so on. You don't want people rewriting this code every time someone needs to implement the blackjack contract. So you can extract this and throw these in the interface as models that each of the functions must satisfy. For instance, a round function must satisfy that betting has greater than or equal to 0 bet, for instance. So if we don't have this, we lead to mass code duplication and pollution. And this helps us reuse the code that we write, maintain a standard for contracts written on our blockchains, and more importantly, enforces trust so that you don't have to know who to trust. You simply know that the contract that you're implementing satisfies these laws. Thanks.
Yeah, great. Thank you, Emily. So we have Carl, and then Ram will be next.
Hello, hello. I'm Carl. I'm an Ethereum researcher. And last time I was here, I was talking about the release of the hybrid Casper testnet and all the trials and tribulations therein. And so a lot has changed over the past year, but one thing remains the same. I'm back again talking about a testnet release. And so I'm happy to announce that the Plasma testnet that we've been working on, myself, Kelvin, Ben, Jing, for the past 2 months, day and night, we've been creating a Plasma implementation for the community, by the community, that you can play with, and it is a lot of fun. And so what is Plasma? This implementation includes not only a easy to deploy operator and get started, at least on my computer it's like 5 minutes, and it also includes a specification, so please read it up and tell me what's wrong with it. It is amazing. It is way too long, and I want you to read every bit of it. And so the final, the Plasma implementation is, what is Plasma in the first place? Well, my God, I'm a little nervous. This lightning talk, I'm not used to this pace. Anyway, what is Plasma? Really quick. Okay, Plasma is essentially a framework for deploying scalable blockchains that are actually secure, and the security is based on a root chain commitment, and that commitment is an accumulator with the Merkle tree. I had more to say than I could, but please do check out this Plasma implementation. It is a test net. It is for you to play with. It is real because we need more real things, and we also need more, people with their eyes looking at the protocols, because my goodness, this is a hard protocol, and research is hard, and my goodness, please, Plasma group. Oh yeah, I forgot. Plasma.group for all of this. Plasma.group.
Thank you. I think we need more lightning talks with that energy level for sure. Okay, so we have Ram and then followed by EJ.
Good afternoon, everybody. I'm Ram Golambudi from ZAG Protocol. So we started actually looking to solve a business problem for many of our customers and enterprises. Right? Most of them want to actually adopt a public chain, but they had two key considerations. While they said, one, they needed transactions to be confidential, source, destination, and value, because they didn't want their competitors to know who they're transacting with often. Second, they wanted smart contracts. And when we looked around in terms of the current blockchains available, public chains, you either had Ethereum, Stellar, wonderful projects, but they handle privacy off-chain, or you have privacy coins like Zcash, Monero, which have limited scripting and smart contract facilities. So that's where we said, okay, can we solve it in a more integrated fashion? So that's where ZAG Protocol origin is. Our approach, our proposal is to have a blockchain which tracks both account balances and UTXOs, very similar to having a wallet where you have your debit card and also cash, and give an ability for the user to move money between his account balances and UTXOs freely, publicly validated. Third is whenever he wants to do an anonymous transactions, use node commitments and zero-knowledge proofs to actually do anonymous transactions. All, again, using zero-knowledge proofs get validated across all the nodes. This gives the flexibility for developers because now there's an integrated chain where they can do both private and public transactions with smart contracts.
Thank you very much. Ooh, okay, so after EJ, we have RZ345.
Hi, my name is EJ Zhang. I'm an associate professor at University of San Francisco. I'm totally channeling Carl here with the speed of my speech. This is a joint work with Jean-Philippe Martin, or JP Martin, known for bar fault tolerance, Byzantine altruistic and rational user tolerance. And the image credit goes to Amhayan. All right, so I want to talk about the gatekeeping attack, and the attack is the existing block producers prevent a new user from becoming a new block producer. And how do they do it? Every proof of stake-based system is asking a new user to make a deposit to a special smart contract or account so that their deposit can be slashed if they misbehave somehow. If the deposit transaction never goes into the canonical block, then the new user cannot become a new block producer. And as block producers, they have a right to do so in some sense because there's essentially no penalty for ignoring a transaction and just leaving it in the pending transaction pool. And why would they do that? If they foresee that their expected block reward is going to diminish when there are more block producers, this is a rational behavior. And when do their block reward expectation goes down, let's say it's a turn-based consensus algorithm or turn-based block producing, then having more block producers mean that it's going to take longer time for me to get my turn. And if it's like a probabilistic choice, proportional to the stake amount. By having a newcomer in, having more stake in total reduces my probability of being chosen as a block producer. So gatekeeping attack is real if it's not well managed, and this is also rational behavior, meaning that it's very difficult unless you make it incentive compatible. So how do we prevent this attack? You have to have a penalty for ignoring a transaction, but how do you impose a penalty if your network is not reliable and or asynchronous? And even if you can actually impose a penalty, how much penalty is enough? If the block reward is infinite amount that they can earn for the infinite amount of time, then essentially what you're doing is that by reducing the probability of being chosen or increasing the time to become a new block, to make a next block, your penalty has to be actually almost infinite. So this is a very difficult problem to solve in asynchronous network and make it incentive compatible. And I'm just going to plug in that this is a new consensus protocol that we're designing to make this attack not so feasible. And if you're interested, I'd be happy to talk.
Thanks very much. Okay, RZ. Okay, last call for RZ. So could we have Phil then, please? Phil, is Phil Chen here? Okay, moving right along. Leftharios, I know he's here. And after Lef, we'll have Elaine. Maybe those were just really lightning talk.
Okay, so I'm here to talk about data management. And I think we all know that right now our data are just hoarded in a data center and are used without our knowledge to do stuff like sway elections and other kind of things. And when we move into the blockchain land, we see some applications that use the word blockchain as magic, like voting on the blockchain or using genomics on the blockchain or storing health records on the blockchain to do stuff. And if you try to actually implement these kinds of protocols, you're going to see that they have the problem that you have to put some data transparently on the chain, and that is not very privacy preserving. So I'm here to talk about a system called Calypso that we have built, where our goal is to create data management under Byzantine adversaries. And the basic idea is that we use some flavors of verifiable secret sharing, and we combine that with blockchain technology to get properties like enabling data owners to share their data, but at the same time be able to maintain control over them. Meaning that if at some point I want to revoke my data, I can just do it. I don't lose them once I put them on chain. I also get the guarantee that I can audit the chain and make sure that I know exactly who accessed my data. So if my data is leaked, I know who to blame, or I know if I can claim payment for someone using my data. And we can actually use all of this cool system while being able to manage our identities in a decentralized way. As a result, there is no actual trusted third party in the system. And if that's not enough, we have other cool applications that can use Calypso. Other than data management, we can build secure decentralized lotteries that don't need any collateral. We can build exchanges that don't need to do order book matching in a centralized way. Or we can do systems like secure drop where you whistleblow in case you do not, in case you have some data and someone kills you, and the Calypso is guaranteed to actually give the data away. Thanks.
Thank you, right on time. Okay, so here's Elaine, and after Elaine, we'll have Alex.
All right. I would have liked to talk about this yesterday in my 30-minute slot, but I would have really worried this would have taken 1 minute, and I wouldn't have known what to do for the remaining 29. So here's a fully functional distributed consensus protocol from scratch. Imagine messages get delivered in 1 second, and every epoch is 2 seconds. In the first second of the epoch, a proposer proposes a block extending the freshest notarized chain it has seen. In the second second of the epoch, I vote on the proposal I've received. If the proposal satisfies certain nice properties, you only need to check 2 very natural properties. Number 1, the proposed block extends from a parent that has already been notarized. Number two, the parent cannot be too stale. It must be reasonably fresh. Okay, when the block gains votes from majority people, it becomes notarized. Notarized doesn't mean final. So what is final? If at any point of time, I see some fully notarized chain ending at 6 consecutive epochs, and I haven't seen any conflicting notarization at these 6 epochs, I will chop off the trailing 5 blocks, and the prefix is final. So that's the protocol. We can prove that it secures against minority corruption in a synchronous model. And with a couple more touches, we can achieve optimistic responsiveness and the robustness property called best possible partition tolerance, which I introduced yesterday. Okay, so I just want to say, okay, distributed consensus, say yes to simple, say no to complicated. Propose, vote, boom, 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 confirm, confirm, confirm. Remember the name of this protocol, it's called Pili. Pili means the sound of thunder in Chinese. Thank you.
All right, thank you. So Alex, and then we'll have Yifan after Alex.
Hi, I'm Alex Lebet. I'm founder of Stable Unit. With my friend James Key, in collaboration with Beam team, we made a prototype of Ethereum Mimble-Wimble bridge, like almost finished. So it's able to convert any ERC20 assets from Ethereum into privacy representation of Mimble-Wimble. It has several real-world applications, for example, for stable coins adoptions. If business accept DAI as a payment method, because it's public, it's the same as showing competitors list of your clients, or if you use DAI as a user, it's same as a posting credit card history in a social network, which might be undesirable. So how does it work? If you have a 15 DAI, for instance, you deposit in a special smart contract piggy bank. And when you're doing, you specify additional information to show you ownership of these funds in Mimble-Wimble. In Mimble-Wimble chain, verifiers, very no slides, sorry. Verifiers have access to the state of a smart contract on Ethereum, and once for a while added into UTXO set these 15 privacy DAI, and you can spend, receive, do whatever you want, and if you would like ERC20 tokens back, you just burn it by depositing in a special like 0 address and show proof of burn into piggy bank and get ERC20 tokens back. Despite simplicity, it has several very interesting properties and advantages. First of all, like Mimble-Wimble is awesome, and you can use all wallets and DEXs and future infrastructure stuff which we're gonna build with minor improvements. And also it's very, very cheap in terms of a gas in comparison with ZK Snark's proof of implementation, like Aztec, for example, like order of magnitude cheaper, and you pay it only twice while you convert it into privacy and while you cash out. If you would like to learn more, just approach me here in conference or find Stable Unit in a Telegram. I'll be happy to answer all questions. Thank you.
Thank you. There were slides, apparently. Okay, so Yifan, and then we have Rylan next.
Okay, cool. You can just look at me. You don't need to read my slide. So hi, I'm Yifan. I'm from Mohawk blockchain. So at Mohawk, what we try to build is a new blockchain where the architect will be like you have one mother chain at the top, and then you can have a bunch of subchains at the bottom. And ideally, we want every DAPP deployed to one of the subchains. And sometimes they can even deploy to multiple subchains if their business logic needs. And one thing we try to achieve with cross-chain IPC is that very often those DAPPs are kind of isolated within that one subchain, so they don't talk to each other. But that's something that we really try to encourage people to do. So that's the rationale behind cross-chain IPC. So that in the future, those DAPPs, you can imagine those subchains, they will form this kind of like a mesh network where those smart contracts deploy on different subchains that can just calling each other across the chains in terms of sending transactions to each other. And so to facilitate that, I'm currently working on this project called Cross-Chain IPC, where you can see I have a list of the engineering challenges for us. For example, like how do we routing those cross-chain transactions correctly and efficiently? And also, should we validate those transactions as the same as a transaction from a real person, a account? Or how we do nonce, should nonce be do like differently comparing to a nonce for a account? Or like at last, like those transactions, they are from chains. So if A chain sends transaction to B chain, then who's gonna pay for those costs that executing those transactions on chain B? All these kind of things. And we have some ideas about how we're gonna implement this. And currently, I'm working on a experimental implementation of cross-chain RPC on blockchain to tackle all these challenges. And I know those ideas are not perfect, so if you are interested in the topic, please come to talk to me offline, and I'll be very happy to talk to you. Of course, you can also send an email to my email address, basically my name at moac.io. Thanks.
Okay, thanks again. Raylan, I have to correct me on that, and then Lisa.
Yeah, that's a wrong spelling, so that's why we need error correcting code, right? So my name is Roland, so I'm the co-founder of IoTEX, which is a startup here, working on the scalable and privacy-centric blockchain for Internet of Things. So there is like one very concrete research problem we face actually when doing this IoTD apps. So the problem is like how a blockchain could authenticate its state to a client. Like the client is so lightweight, we call it like the lightest client. It has no previous states of the blockchain. Also, it has very limited computation resource, storage resource, networking resource. How would you do that efficiently with low cost and also in real time, right? So that's a very very typical research challenge. So to overcome this issue, like we design a crypto protocol, we call it a B4R, meaning like Blaze for reward. So the intuition behind this is pretty simple. So we give like the full nodes in the network a new role. Basically, they generate a Blaze for blocks. So for blocks and states. So basically, Blaze is like a new succinct proof to us testing certain amount of effort has been spent on certain type of data. That means like this can be constructed using VDF, using password hashing, and also using some even hash function, for example. And then this Blaze will broadcast in the network. The lightest client will pick up these Blazes and try to verify if this is correct, and also assess the effort behind all these Blazes, right? Collected efforts. So if they are certain about like basically like the more effort it has been spent on this data associated with, the more trust like the client can put into the data. So that's how this client authenticates these block states. So there would be like a very interesting problem would be like how would you make this ASIC or maybe hardware resistancy. So that's why we also introduce like crypto agility into this design, which means like the Blaze can be generated by different constructions, different like password hashing function, even like a VDFs. So also we introduced a concept called like a scarcity when it comes to assessing like how effective and also how much effort it has been put into that Blaze. So like the full paper will be released soon, I guess probably next month or even like in a few weeks, and we'll be happy to talk more about details. You can find me anywhere. All right, thank you.
Thank you. Okay, so we have Lisa and then Aniket.
Cool. Cool. Hello, my name is Lisa. What I'd like to do is walk you through an alternative way of looking at zero-knowledge proofs. But in order to do that, first we need to go through a quick primer on the nature of reality. So first, we live in a multiverse. Physicists will recognize this as the many worlds interpretation of quantum results. From this, experiments in reality becomes a process of locating the nature of reality that you currently inhabit of all possible. I'll say that again. Of all possible realities, which do you presently inhabit? So the nature of existence, then, is a process of fixing or discovering the particular nature of your reality. There are a number of ways to fix the reality that you exist in, two of them being observation and time. Okay, so what does this have to do with zero-knowledge proofs? I'm so glad you asked. So let's consider a range proof for a single bit. It's the construction of two values such that you can prove that you know the discrete log of one of them. In other words, the existence of such a proof fixes our reality to one of two options. And the proof is a commitment to one of the two in this set of possible realities. So it is possible to observe this reality via the revelation of the blinding key. An outside observer can verify that we exist in the reality where either of these statements is true. However, only a person with the blinding key knows for certain the actual nature of the reality that we presently exist in. Thus, the crafting of zero-knowledge proofs is a practice of obfuscating the observability of the nature of our present reality while fixing it definitively via a bounded set. So in another way, a zero-knowledge proof is like a Schrodinger's cat, with the caveat that selected parties are privy to knowing the cat's fate, and the rest of us are not. Thank you.
Okay, Aniket is here, and then Shashank.
Hello, everybody. My name is Aniket Kate. I generally work on different things in privacy with blockchain, but today I'm going to talk about one particular topic which is very close to my heart, that is credit networks. So you might have heard about companies like Ripple and Stellar, or maybe a project like Trustline Networks, where the idea is we can build such networks of a graph of IOU links between different networks and perform transaction that goes from one node to somewhere else through such transitive links. And they provide different values which go beyond payment channels, because we can create depth links and other things. So they have been found to be useful, and Ripple and Stellar IOU networks demonstrate that there is a huge value in this space. But through our research, we try to ask questions and try to bust some myths in that case, in the sense that one of the key things that we want to study and demonstrate that we don't require any kind of tokens in such credit network systems, and they could be built in a completely distributed manner. So as one of the intermediate experience, what we did is that can we build such a system on Ethereum and have a complete contract which is ready and built, and all the transaction value costs that are going to occur are just basically the gas value that we observe in that space. And we did that. It did not require any token. It's just gas values for Ethereum implementation could be implemented and scaled for the second layer solution. And what we observed that these are the values from maybe I think November or something like that, that indeed if we just rely strictly on the gas values in Ethereum, the values for most of the things which are decided by that value are significantly lower, even for things like as path-based transactions as they happen on Ripple as compared to as they happen on our Ethereum-based smart contract. The values are not huge difference, and we don't decide them. We just let the market decide that, and we find this to be a nice, thoughtful experience. More to know about what we did, our contracts, as well as information about what research we do, go to the transitivenetworks.com. And I want to end my talk by saying that, in fact, even for such a credit network, implementation based on such Ethereum or any such blockchain is not necessary. Such systems could be built just purely having two-phase commits, or what we can call as local consensus. If you are interested in this space, come and talk to me afterwards. Thanks a lot.
Thank you. Okay, last two speakers will be Shashank and then Remco.
All right, hello. Yeah, hi. I'm going to take maybe like a minute and a half. Just quickly, we were originally trying to build essentially a decentralized high-frequency derivatives platform. And when we started building that a couple of years back, we realized that building it on the Ethereum network was very impractical. And the impracticality came from multiple things, including scalability, the costs attached, the high frequency, and so on and so forth. So we segued into essentially trying to build a layer 2 solution and didn't want to reinvent the wheel, so we took where Plasma was and started building on top of that. So we have a version of Plasma called Gluon Plasma, which has been out there on the ETH research community, and we've received some fantastic feedback from people on that. And we have a testnet running with this Gluon Plasma version for the last 3 months, and we're ready to go mainnet pretty soon. The idea of this version of Plasma is based on an account-based model as opposed to UTXO-based model. But it does build on most of the things that Plasma Cache, Plasma MVP, and a bunch of other Plasma variants have done. So it's not completely fresh. It just kind of improves on that and adds a few additional things. It is provably secure. There are things that are in our paper. I don't have enough time to talk about it. I think there were a couple of slides, but don't worry about it. You can just maybe Google for leverage gluon plasma, or just go to E3 search and look for gluon plasma. You'll probably find the links. And then last but not the least, we'll be open sourcing it in the next few days with the implementation, with the code. And we'd love to get feedback. All the feedback we received so far is fantastic. That's how we've been able to improve. We'd love to hear more. And folks who are interested in plasma and the plasma community, I would love to talk to you folks during this conference as well. I know that many of you are here. I've spoken to some of you, and many more of you are interested in this space. So find me, and we can have a good chat there. Okay. Thank you.
Okay, keep it going. Remco will be our final speaker.
Hi, I'm Remco, and I have a polynomial. I'll prove to you that it has degree at most n. First, I generate a large set of x coordinates, and I evaluate the polynomial in this set. Now I create a Merkle tree of these points and give you the Merkle root. If you interpolate these points, you can see that, that the degree is as I claim. However, this set is large. Now, let's look at a fun property of polynomials. If I negate the variable, this is as if I negate every odd coefficient. If I sum it back to the original polynomial, I've effectively filtered out all the odd coefficients, and I'm left with the even ones. With a little bit of algebraic manipulation, I can use this to create a linear combination of the odd and even coefficients. So now you give me a random value beta. And I do this coefficient folding to create a p prime where the new coefficients are a linear combination of the old coefficients. However, the degree of the polynomial is now half. Another thing to observe is that I've only used values that were already in the set of points that I committed to. So now I have a new set of points that I can commit to with a new Merkle tree, and I can give you this commitment again, and we're back to where we started. So we can repeat this process, halving the degree at each step, until we're left with a constant, and I can just give you the constant straight away. This works for a set of x coordinates such that when x is in the set, the negation is also in the set, and this is closed and the squaring. This set is the roots of unity, the same as you use in the fast Fourier transform. Now, you have all these Merkle roots that I committed to, and you know the betas that you gave me. You can now point check different points of this, this set of value of these points, check the computations, and convince yourself that I did them correctly. The Frey theorem will tell you that you need actually very little of these point checks in order to convince yourself that my polynomial is indeed of degree at most n. Thank you.
Okay, that's it. So it's now officially lunch. Thanks everybody who stuck in here, and I believe we're back on at 2 p.m.